in quantum physics. We are very happy to have Mayuko Yamashita from the University of Tokyo here, and she will talk about index theory on manifolds with fiber boundaries and its applications.
Thank you for the introduction, and thank you for inviting me here, and so thank you for giving me the opportunity to talk in the last seminar of this conference. So I'm going to give you my explanation about my ongoing work to give an application to topology on singular spaces using non-commutative geometric ideas. So I will start with the introduction. Basically, I'm working on index theory and non-commutative geometry. And for me, non-commutative geometry means to extend the Atiyah-Singer index theory to more general settings using operator algebra and K-theory on that. So first, let's recall something about Atiyah-Singer index theorem. So this is a very classical important result, which is a result about closed manifold with even dimension. And you consider elliptic operator acting on some vector bundle over M. Then so this is elliptic operator. Then it can be shown that this operator is Fredholm. And Fredholm index, you consider the Fredholm index of this operator, and Atiyah-Singer index theorem computes this number in terms of topological data of this manifold and these operators. So this theorem is very important because many geometric important operators arise as elliptic operators. So there are examples such as Drum operator, which gives you the Euler number of this manifold, and also a spin-Dirac operator if this manifold has spin structure, and this has an application, for example, for the positive scalar curvature problem for manifolds. And but in this talk, I'm going to talk about signature. So let me recall the notion of signature for closed manifold. This is a topological invariant for 4K dimensional manifold, which is closed and oriented. So the definition is as follows. Since this manifold has 4K dimension, you consider the middle dimension cohomology and cup product to give the symmetric quadratic form. So it gives you the signature in the sense of quadratic form, and this number is defined to be the signature for this manifold. And this is, by definition, obviously a topological invariant for this thing. And it is related to this index theory because this number is expressed as an Fredholm index of an elliptic operator called signature operator. So signature operator is, as an operator, it is just a D plus D star acting on exterior bundle over M. And this operator is self-adjoint, so its index itself is not interesting. So this is self-adjoint. But this bundle has a Z2 grading structure given by Hodge star. And this operator is odd with respect to this Z2 grading, which means that you have the following form. And if you talk about self-adjoint operator, which is odd with respect to some Z2 grading, you actually talk about the index of this part, which is non-trivial in general. So, and by Hodge theory, you have the identification of these two things. Theory. This index, you can show that this index coincides with this. No. The signature. So this was something about closed manifold, and today I'm going to talk about manifold with fiber boundaries and index theory on it. So let's define the manifold with fiber boundary. The picture is like this. You have a compact manifold and it has boundary, and on the boundary you have a fiber bundle structure. So M is a compact manifold, and we assume it is oriented. And pi is a fiber bundle structure only defined on this thing, this part. And so I also assume that this is oriented fiber bundle. And for simplicity, I assume that in this talk, this dimension assumption. So Y is odd dimensional and M is even dimensional, which means that the fiber of this fibration, denoted by Z, is even dimensional. So this is a manifold with fiber boundary, and natural question is going to be how this structure arises in nature. And I have two examples in mind. One is a singular fiber bundle. Of course, there are many definitions possible for singular fiber bundle, but such a structure arises in many places in mathematics. But so many definitions have in common the following structure. So there is a manifold M, smooth manifold M, and smooth manifold X, and smooth map between them. And X has some small subset, let's call V, on which the pi is something singular, and on the complement of this V, you have a smooth fiber bundle structure restricted to by pi. And in this case, you consider the tubular neighborhood of V, tubular neighborhood or just neighborhood of V, which I call U, such that U bar is a manifold with boundary. And the inverse image is a subset mu. And in this case, you get a manifold with fiber boundary by restricting this pi to the boundary of this thing. And the second, this was a singular fiber bundle structure. And so the second example is going to be stratified pseudo-manifold, which is a kind of manifold with singularities. Stratified pseudo-manifold has a notion of depth, which gives you how complicated this structure is. And the simplest case of depth 1 corresponds to the manifold with fiber boundary as follows. Stratified depth 1 means that manifold with H-type singularity. So this means that your M hat, your space M hat, is divided into regular part, and as a set, this is a disjoint union of some open manifold and closed manifold. And near Y, you have the following structure. You have the cone bundle structure over some smooth manifold Z. So this is related to actually one-to-one correspondence between manifold with fiber boundary topologically, because if you have a manifold with fibered boundary, you can crush the fiber of the, so crush the fiber only on partial M to get the, so M hat, you get by this. And of course, conversely, if you have this thing, you can cut the neighborhood of Y to get a manifold with fibered boundary. So I'm going to switch these two pictures in this talk. So this was the two examples in my manifold.
Limitations in mind?
I'm going to talk about it soon. So this was the I explained here how they arise in nature, and so of course, as I said, index theory on manifold. I'm going to give index theory for manifold with fibered boundary, and my hope is to give something interesting for this kind of structures. So, and index theory or elliptic theory on manifold with fibered boundary this is not a new topic. This has started by Mazzeo and Melrose in 90s by introducing suitable pseudo-differential calculus on manifold with this structure called the 5 calculus or edge calculus. But and since then there have been many works to understand the elliptic theory or pseudo-differential operators on this kind of structure. But their approach are mainly analytic in nature. And my goal here is to give a topological approach to index theory on such spaces. And also give an application to these examples. And actually, I have a preprint about topological approach to these spaces. And in that preprint, I gave a application to this example 1, which so concretely, I gave a localization result for manifold with singular fiber bundle structure. But I'm currently working on this part, and so it is not on my previous paper. So, so I'm going to talk about this part in this talk. So, application to signature on manifold with edges. And I hope to explain how I use sister algebras and K-theory for giving a topological approach to these things. So the rest of the talk is going to be follows. First of all, it is better to have problem in mind. So I give more precisely the signature problem on manifold with edges. And secondly, I will describe the general theory about this part. And finally, I will apply this general theory to this problem and give a solution to this problem. And also, I will talk about future works. So let's start with describing the problem I have. So let M hat be a manifold with edges. Then you want to consider signature of this thing, but it doesn't make sense in general. So not. You can see this as follows. First, you consider the cohomology group of this thing, but in order to make sense of the quadratic form, you needed a Poincare duality for this cohomology, but this is not a manifold, so M hat doesn't have Poincare duality in general. And also from analytic side, you try to construct a D plus D star on the regular part of this thing, but note that in order to construct this D star, which is a formal adjoint of this thing, you needed to choose a Riemannian metric on M. And in this case, your regular part is open manifold, so there are many choices of metrics which are not quasi-isomorphic. And there are some nice classes, some natural classes of metrics you can consider on this kind of thing. In this talk, I'm going to talk about two kinds of metrics. Incomplete edge metric and complete edge metrics. So just I draw this picture only here because I use it always. So incomplete edge metric is defined as follows. So in order to make sense of this thing, you have to, this is technical thing, but you have to choose a splitting. So near the boundary. And also, so choose some Riemannian metric and fiber-wise Riemannian metric on this thing. So, and also, so this R factor is coming from choosing a boundary defining function which is 0 and positive in the interior. So, using this incomplete edge metric is written as follows. Under this decomposition. And, x2. And complete one is this thing. So this means the following. This incomplete edge metric is the natural metric. If you draw a picture like this, this is a conical metric near the y. And this is incomplete in the interior. But complete edge metric is something conformal to this thing. And this is complete metric. And you can consider this as follows. You reach near the boundary. And if you reach near the boundary, you take an adiabatic limit of the boundary, which is the deformation of metric only extending metric on the base direction. So these are two kinds of metrics we can consider. And correspondingly, we consider the signature operator associated to these metrics. And of course, this makes sense as a symmetric operator, but the problem is that, for example, you consider the incomplete one, and this is not essentially self-adjoint in general. So it means that you have to choose a closed extension of this unbounded operator, and the Fredholm property or Fredholm index depends on such a closed extensions. And also you consider this one, which is always essentially self-adjoint. But the problem here is that this operator is never Fredholm. Because you can consider as follows. If the simplest case, if y is a point, it is equivalent to the cylindrical metric. And if your manifold has a cylindrical end, the signature operator is not Fredholm. So this is, so from this, we think that it is hopeless to think about the signature type invariant for singular spaces. But there is a nice class of pseudo manifold called Witt spaces, which is still an interesting class. So this manifold is fibered boundary satisfies Witt condition if and only if this fiber, so fiber was Z, satisfies this simple condition. So the middle dimension should vanish rationally. But so this is very simple assumption, and there are many examples. And so the corresponding M hat is called the Witt space of depth 1. There is a notion of Witt space of higher depths, but I don't use it here, so let's concentrate on the depth 1 case. And the point is that if this satisfies Witt condition, you can somehow make sense of signature as follows. Suppose this is Witt space, and cohomology, you consider the cohomology, which is for stratified pseudo manifolds, there is a cohomology theory which is called intersection cohomology, and for Witt spaces, it satisfies Poincare duality. So I'm not going to talk about intersection cohomology today, but you can just consider you have some nice cohomology theory for this space, and it satisfies Poincare duality. So using this, you can consider the signature. And from analytic side, you have the following. If you use incomplete metric and with some technical assumption on metric, it can be shown that this is essentially self-adjoint and Fredholm. This is a result by Chiga. And there is a fact that this index coincides with signature by middle perversity, intersection cohomology. And the problem here is that this operator is very analytically difficult to analyze, analytically difficult. So for example, the fact that this is essentially self-adjoint and Fredholm is non-trivial compared to the closed manifold case. But actually, I realized that for Witt spaces, I can use my general theory about topological approach to index theory on manifold with fiber boundary to give a canonical number. And actually, this coincides with this thing. So my goal here is to give an alternative definition. Give for this signature, and which is without difficulty, analytic difficulties, and also more suited to K-theory approach. So this was the description of my problem. And let's move on to the general theory. So let M pi be a manifold with fibered boundary, and I don't assume anything about Witt condition. So this is just a manifold with fibered boundary. And so the goal of this section is the following. Given a manifold with fibered boundary and this thing, where manifold is fibered boundary satisfies, I assume this condition. So d pi is the fiber-wise signature operator. For this boundary fibration. So this is a family of elliptic operator parameterized by y. And this has a family index defined on the K-theory of y. So I assume that this is 0 in this K-theory. And also, this additional information here is an invertible perturbation of d pi. I'm going to talk about define invertible perturbation soon, but so given for these data, I'm going to define signature m. So this integer, which is a kind of signature defined by a boundary condition given by this invertible perturbation. So let's describe the notion of invertible perturbation. So let d pi be some family of elliptic operator, first order elliptic operator, and odd with respect to some Z2 grading and self-adjoint family. And d pi tilde is called an invertible perturbation if this is a family. This is also a family parameterized by y, and this has the following form, where is a invertible perturbation if and only if this A pi is a lower order family of pseudo differential operators which satisfies the same additional symmetry. And also, of course, I assume that d pi tilde is invertible family. And this is the definition of invertible perturbation. And the fact is that the existence of invertible perturbation is equivalent to the vanishing of the family index class. This kind of lower order perturbation doesn't change the family index class, and invertible family has index 0. So if you have an invertible perturbation, it is obvious that this family index is 0, but converse is also true. So this is the invertible perturbation. So let's define this number. So this number has a nice definition using groupoid and C-star algebras, but it has to do with the preparation about groupoid pseudo differential calculus. So I'm going to first give you the definition without using any C-star algebra. So first, you recall that you have this complete edge metric. And correspondingly, you form the signature operator here. And near the boundary, since you have the following that decomposition of the tangent bundle, so you have the exterior bundle is decomposed like this. And so you can make sense of the operator acting on this bundle near the boundary. So using this, this is a zero order operator. So you consider this lower order perturbation of this operator. Here this chi is the cutoff function near the boundary, so it is something like this. So this is a lower order perturbation of this complete operator. And because that this complete operator is not Fredholm. But using this perturbation and the fact that the pi tilde is an invertible family, you can show that this is Fredholm. And you define this signature to be the index of this thing. So this is a very short definition, but I didn't say anything about how you show the Fredholmness of this thing. And so in order to understand this operator, you have groupoid pseudo differential calculus is very useful. So from now on, I'm going to talk about groupoids. So I have to be very ambitious here, so because I cannot give the full account of groupoid pseudo differential calculus and Fredholm theory on such a thing. But the reason for doing this, trying to do this here is the following. First of all, I have to convince you that this definition I defined is very topological and without any analytic difficulties. And second, using groupoid picture, it is very easy to generalize this to generalize this theory to many complicated situations. So this is related to the future work part I'm going to talk about in the last part of this talk. So let's start with the groupoid pseudo differential calculus I briefly describe. So let G be a D groupoid. And associated to it, you can consider differential operator on D groupoid and also pseudo differential operator on D groupoids. This is a generalization of translation invariant operator on D group. And also, if you have a operator here, then you can make sense of the principal symbol of this operator. In order to do this, you have to have a corresponding object to the tangent bundle of a manifold, which is the algebroid. Associated to D groupoid. And then this is a vector bundle over the object space D0, and you can form the cosphere bundle, which is a sphere bundle over the Z0. And from pseudo differential operator, you make sense of the principal symbol, which is a continuous function over this cosphere bundle, total space of cosphere bundle. And ellipticity, so D is elliptic, is defined by the invertibility of this principal symbol. And so you should have some simple example in mind. Let M be a closed manifold, and you consider the pair groupoid. So the source map sends this to the pair XY to this part, and target map maps this part. And using this groupoid, you recover the usual notion of pseudo differential operator and principal symbol as follows. So differential operator of this groupoid is shown to be equivalent to differential operator of this manifold. And so in this case, so the algebroid is equal to the tangent bundle over M, and principal symbol is equal to the usual thing, which is a function of the cosphere bundle over M. And there is a generalization of pseudo-differential extension. So let G0 be a compact. Let's assume this. Then you have this pseudo-differential extension. This is a norm completion of the zero-order pseudo-differential operator on G, and this is a symbol map which sends the operator to elliptic, principal symbol, and the kernel of this is the C-star algebra of this Lie groupoid. And from this exact sequence, you get the boundary map. So let's call this index map, because this, so invertible principal symbol defines a class in K1 of this thing, and its image is defined to be the index class of this operator. So this recovers the, so in this example, you have the following. So K0 of C star of pair groupoid. C star algebra of this groupoid is the compact operator algebra of this M. So this is the, this case theory is D, and the so invertible principal symbol class is sent to the usual Fredholm index of these things. So this is a brief account about groupoid pseudo-differential calculus and Fredholm theory on it. And this recovers many interesting construction in non-commutative geometry, because, for example, you have a foliation on a closed manifold, then you consider the holonomy groupoid associated to it, and differential operator on this groupoid is equivalent to longitudinal operator on foliation, and its index class is a K-theory class of C-star algebra of holonomy groupoid, which recovers the result by Kohn and Skandaris. And also, if you have a covering, universal covering of a closed manifold, then you consider the fundamental groupoid, and so invariant operator on this universal covering defines a class in this C-star algebra, and this groupoid is Morita equivalent to the group gamma. So this is the K-theory of C-star gamma, and it is the same thing as higher index. So, and I'm going to apply this machinery to manifold with fiber boundaries. So let's return to the situation of manifold with fiber boundary and consider the complete edge metric and associated signature operators. Then you have, there is a known construction about Lie groupoid, which is suitable context to treat these kind of things. This groupoid has the following structure. Here, this is a groupoid over M. And here, this is a groupoid, pair groupoid on the interior. And this is a groupoid on the boundary. And so this boundary groupoid has a structure of product and with this group bundle over Y, and this pair groupoid, fiber-wise pair groupoid over this of this fiber bundle. And so DE is shown to be the differential operator over this groupoid. So, and moreover, it is the elliptic operator in the sense here. And so applying this procedure to this operator, you get the index class of which is takes values here. But this is not the right thing, because I want to have the index here in the interior groupoid. So in order to do this, the ellipticity of this operator is not enough, and it turns out that you also have to have the invertibility of the operator restricted to the boundary. So this is explained as follows. You define the following C-star algebra. Here, this is a principal symbol map, and this is just a restriction map. And you can write a extension just like this. To get an index map from K1 of this algebra to K0 of the interior C-star algebra, which is equal to Z. And if you have a invertible element of this algebra consists of invertible symbol on the whole GE, and also the invertible operator on this boundary of groupoid. So something like this defines a class in K1, and it is sent to the Fredholm index in the interior. So let's return to the operator DE, which is a signature operator, and this has a restricted to the boundary. You have the following form. Here, this is a Hodge-star operator on the fiber-wise, and the point is that this operator and this operator anti-commutes. And so, and this operator is not invertible operator, as I said before, but recall that we had the invertible perturbation of this family, and using this, you define this perturbation to be this thing. This part and this part anti-commutes, and this is invertible, so this is an invertible operator. So this defines a class like this, and the definition, actual definition of my signature was index map applied to this pair. And it is easy to see that this definition coincides with the previous definition I gave. And I understand that this does not make sense for most of you, but what I wanted to say is that this definition didn't have to do with any analytic difficulties, and you just have to specify what groupoid you are working on and what invertible operator you consider. So let's use this thing to solve the problem I described. So recall that we had a notion of Witt spaces. We were considering manifold with fibered boundary such that the middle cohomology vanishes for the boundary fibration. So in this case, you have the canonical choice of invertible perturbation for boundary fibration. Let's denote this by Witt perturbation. Of course, this has the role of boundary condition of this signature. So if you change the invertible perturbation here, you change the signature obtained here. So the canonical choice is described like this. First of all, it is enough to construct the following. Since the family of signature operator has a well-defined kernel bundle, you don't think about the orthogonal complement of the kernels, and just think about the kernel bundle. So enough to construct an automorphism of this bundle, which is self-adjoint and odd with respect to this Z2 grading, which means that this automorphism should anti-commute with the Hodge star. And also, since you are considering the family of signature operator, which is D plus D star, this kernel bundle is isomorphic to the fiber-wise fiber-wise harmonic form bundles, which is a finite dimensional bundle over Y. So let's have this in mind and construct the U. This is very easy to define as follows. So this is defined to be plus identity, just identity on the harmonic forms with degree less than middle, and minus 1 on the higher degree. And this is shown, it is easy to see that this is self-adjoint operator, automorphism, and also this anti-commutes with Hodge star, fiber-wise Hodge star. And the point here is that I used the Witt condition because this middle dimension harmonic forms does not exist for Witt spaces. And in general, in order to make an invariable perturbation, you have to choose a Lagrangian subbundle of the middle cohomology, middle harmonic forms, and this is the exactly the non-trivial part of the family index class. So from this, you define the Witt perturbation to be the d pi plus this automorphism. So you consider the signature defined by this perturbation, and the proposition I was able to show is that this coincides with the index defined by incomplete edge operator. And of course, in order to show this, you have to do something complicated analytically because this operator is analytic, difficult operator. But in this way, I was able to give an alternative definition without any analytic difficulties. And also, the gain here is that I was able to show a formula for this. Namely, you want to compare a signature for manifold with boundary. So, in general, manifold with boundary, and just so forget about the fiber bundle structure. You can make sense of the signature in terms of the this image. And non-degenerate quadratic form defined on this image. And this is well-known construction of signature for manifold with boundary. And you want to compare these things. And actually, this coincides with some invariant I cannot define here. That is tau invariant. This is an invariant for 4k minus 1 dimensional fibration, and it is defined in terms of Rayleigh spectral sequence of this pi. And this formula, I showed this formula by elementary way, and Rayleigh spectral sequence is related to the adiabatic behavior of the boundary, so Laplacian of the boundary. And actually this is actually known result, and this is not a new result, because so signature with respect to the intersection cohomology and comparing this number, this was known by, for example, Chiga Dai. But the point here is that assuming the result that this coincides with this thing, this recovers the result by Chiga Dai, and I was able to show this very elementary way, and it can be considered as an alternative proof for this fact. So this was something about usual usual Fredholm index, which takes values in Z. And also, as I said before, if you have a groupoid picture in mind, it is very easy to generalize this in many ways. So suppose that M hat has a covering. Galois covering by some group which is allowed to be infinite group, then you can consider the signature which takes values in K0 of C star of gamma. This is a higher index version of the Witt signature. And this is, we can define. This uses groupoid as follows. You can actually define very easy way that groupoid which has a structure like this this is a fundamental groupoid in the interior, so this gives the higher index. I wrote something here, and this part is exactly the same thing as the previous GE. So invertibility on this part is exactly the same thing. So using this groupoid, you get automatically higher index corresponding to this invertible perturbation. And actually, in this direction, there is a work by Alvin, Mazzeo, Rishnam, Piazza, very recently, that they use the Mishenko-Fomenko bundle and make sense of the higher signature for Witt spaces. And this, for this, they use the incomplete edge metric. So, and using this operator, they define a higher signature counterpart. And this thing coincides with this my signature. And of course, they have to do with some analytic difficulty in their paper. So my point is that I can define this thing without any analytic difficulty in the same way for higher signatures. And actually, their work is for any depth. I was talking about only depth 1 case in this talk, and you can actually construct a counterpart for my construction in the higher depth case, which is so high. In the higher depths, you have the something like this kind of structure. You have the cone bundle, and the fiber is also the stratified space. And the corresponding thing is a manifold with corners, and each boundary hypersurfaces have fiber bundle structures, and on the corners there those fiber bundle structures have some compatibility conditions. So and it turns out that you can construct a groupoid associated to such structures. This groupoid was constructed by Debord and Lesk and Roshan. And using that machinery, we can construct a Witt signature defined by perturbation on the hypersurfaces. And also, other future work. So there are many directions I'm considering about this construction. First of all, this construction is very easily generalized to the case where manifold M has a boundary, and this is a foliation, not a fiber bundle structure on partial M boundary. This is, of course, the generalization of this thing. And for some technical reason, I have to assume that this is Riemannian foliation. And you get a corresponding index theory for manifold with foliated boundaries. Actually, I want to do away with this Riemannian condition, but I'm currently thinking about it. And also, more generally, you can consider this kind of thing. H is a foliation on M. So this is, you have also foliation on the interior of this manifold, which is transverse to the boundary. And F is a foliation on partial M, and H restricted to this thing is contains this one. So this is the generalization, further generalization of this thing. And also from this situation, you can consider the index theory out of it. And also you can also consider something like M hat has a covering, and also the fiber of this thing has another covering. Then you get a relative higher index. And this is a generalization of higher index, which is a very hot topic in positive scalar curvature problem. And for example, Weinberger and Chan and Yu, and also Kubota has provided recent results about relative higher index. And their result corresponds to the case where pi is just y is just a point. But you can consider this fiber bundle structure or possibly foliation structure and get more interesting generalization. So I stop here. Thank you.
Thank you very much. Well, let me put myself in the position that I see everybody. Any comments or questions? I have only very speculative questions. It's a bit far from my field, but can you do anything in physics one is often interested in Lorentzian manifolds with hyperbolic operators on them. And I think, I'm not sure, but there is some generalization of index theory to that setting. Other people might know better. I'm not sure, does it fit in your setup?
I don't know about this, but your manifold is complete and some structure on the end.
Think of any. One would typically be interested in what's called globally hyperbolic. So it's a Lorentzian space-time, maybe with a singularity like black hole or things like that, to connect to physics. But I had the feeling in many areas you will look at elliptic and Riemannian, so there are certainly differences. I just wonder that maybe on operator algebraic level these differences can be overcome, or I don't know. Speculative, as I said. Yeah.
Is it related to the manifold with hyperbolic end?
And I wouldn't know. It would typically not be something with a boundary.
So I mean that not boundary, but the imposing something like the complete edge operator, complete edge metric is just putting the boundary away with some deformation, nice deformation on the metrics. So it should be stated in terms of complete metric, complete manifold.
Okay. Basically, I can probably point you to where people worked on index theory in a Lorentzian setting, and maybe it fits in your setup. I don't really know, but that might be interesting to connect to field theory.
Actually, I think I don't know about how their Mazzeo and Melrose work arose, but I think they are interested in such manifold with hyperbolic end. And this structure comes from physics. So I'm sorry because I don't know anything about physics, but maybe it is possible to formulate this using groupoids and say something interesting about index theory on such places.
Any other questions? Comments here? All questions answered. We proceed to coffee. Thank you very much. I can only give you the name of the person who I think worked in that direction is Christian Baer.